James Webb just caught a black hole, growing faster than it should be able to in late 2023 while the James Webb Space Telescope was quietly working through a list of targets that most astronomers considered leftovers. It locked onto a faint smudge of light that had been sitting in an old X-ray catalog for years. Nobody expected much. The object was so dim that it did not even show up in previous optical surveys. But when the data came back to Earth, it revealed a black hole doing something that violates the most fundamental speed limit in astrophysics. It was feeding on matter 40 times faster than the laws of physics say should be possible. Not 40% faster, 40 times faster. This is the story of the black hole that broke the rules, and why it might finally answer one of the biggest questions in the universe. Before we dive in, if you love stories about the edge of what we know, hit subscribe. Every week we explore the discoveries that are quietly rewriting our place in the cosmos, and you do not want to miss what is coming next. To understand why this discovery shocked astronomers, you first need to understand something that sounds like a contradiction. Black holes, the hungriest objects in the universe, have a maximum eating speed. Ask most people how a black hole works and they will describe a cosmic vacuum cleaner, an object that devours everything around it without limit. The reality is stranger. A black hole cannot simply swallow whatever it wants, whenever it wants. There is a built-in throttle, and it comes from an unlikely source: light itself. Here is how it works. Matter does not fall straight into a black hole. It spirals inward, forming a swirling disk of superheated gas called an accretion disk. As that gas spirals faster and faster, friction heats it to millions of degrees, and it begins to glow with unimaginable brightness. A single feeding black hole can outshine every star in its galaxy combined. But all of that light pushes outward. Photons carry momentum, and when trillions upon trillions of them stream away from the disk every second, they physically shove against the incoming gas like a wind blowing against someone trying to walk into a storm. The faster a black hole feeds, the brighter it burns. The brighter it burns, the harder that radiation pushes back against the infalling matter. Eventually, the outward pressure of the light exactly balances the inward pull of gravity, and the black hole simply cannot pull in food any faster. Astronomers call this ceiling the Eddington limit, and the man it is named after deserves a moment of his own. Arthur Eddington was a British astrophysicist working in the early 20th century, and he was arguably the first person on Earth to truly understand how stars work. In 1919, he led the famous eclipse expedition that measured starlight bending around the sun, the observation that confirmed Einstein's theory of general relativity and made Einstein a global celebrity overnight. But Eddington's quieter contribution may have been even more important. Sitting with pencil and paper, he worked out the physics of radiation pushing against gravity inside a star. And in doing so, he defined the maximum brightness any object of a given mass can sustain. He derived this decades before anyone had proof that black holes were even real. He was describing a speed limit for objects that, as far as anyone knew at the time, existed only in the strange mathematics of relativity. And yet, his century-old calculation became the foundation for how we understand the most extreme objects in the cosmos. Gravity pulls matter in, light pushes matter out, and the balance between them sets a hard maximum on how fast any black hole can grow. For 100 years, that limit held. Astronomers found black holes feeding at half the limit, at 90% of the limit, occasionally nudging slightly past it in brief bursts. The Eddington limit was treated almost like a law of nature, and that is exactly why it became the centerpiece of a mystery that has haunted astronomy for 2 decades. The mystery is this: when astronomers point their telescopes at the most distant reaches of the universe, they are also looking back in time, because light takes billions of years to reach us. And in that ancient light, they keep finding monsters. Supermassive black holes containing hundreds of millions, even billions of times the mass of our sun, already fully grown when the universe was less than 1 billion years old. Think about what that means. The universe is roughly 13.8 billion years old. These giants existed when the cosmos was a toddler, barely 5% of its current age. Here is the problem. Black holes are supposed to start small. When a massive star dies and collapses, it leaves behind a black hole of maybe 10 to 100 times the mass of the sun. That is the seed. For that seed to grow into a billion solar mass giant, it has to feed. And if the Eddington limit caps its feeding speed, the math simply does not work. Even if a stellar seed fed at the absolute maximum rate, without pausing for a single moment, there was not enough time since the Big Bang for it to reach the sizes we observe. It is like finding a full-grown blue whale in a pond that was dug last week. The whale is real, you can see it, but it should not have had time to exist. Cosmologists have called this the seed problem, and for 20 years it has been one of the most uncomfortable open questions in astrophysics. Every new deep survey made it worse, turning up earlier and bigger black holes. Something about our story of how the universe builds its giants was missing a chapter. Either the seeds started far bigger than we thought, or somehow somewhere, black holes were cheating the speed limit. Which brings us to a researcher named Haiwan Su and a list of targets that almost nobody wanted. Su is an astronomer working with the International Gemini Observatory, and her team had been studying a peculiar set of objects from the Chandra X-ray Observatory's survey of a patch of sky called the Cosmos Field. These objects were strange. They blazed brightly in X-rays, which is usually the calling card of a feeding black hole. But when astronomers looked for them in visible light, there was almost nothing there. Just darkness. For years, these sources sat in catalogs as question marks. Too faint for ground-based telescopes to study, too weird to explain, too easy to ignore. The James Webb Space Telescope changed that. And to appreciate why, you need to understand what an absurd machine Webb actually is. Webb's primary mirror is over 21 feet across, so large that no rocket on Earth could carry it in one piece. So engineers built it from 18 hexagonal segments coated in a whisper-thin layer of gold, and designed the entire telescope to fold up like a piece of origami. It launched folded, flew nearly 1 million miles from Earth, and then unfolded itself in space through a sequence of hundreds of deployment steps, any one of which could have ended the mission if it failed. There was no repair option. The telescope sits 4 times farther away than the moon, far beyond the reach of any astronaut. Every single step worked. The reason Webb lives so far from home is temperature. Webb is an infrared telescope. It detects heat. And that is exactly the kind of light you need for hunting the early universe, because as the cosmos expands, it stretches the light traveling through it. Light that left an ancient galaxy, as visible light arrives at our doorstep, 12 billion years later stretched deep into the infrared. To see that faint warmth, the telescope itself has to be colder than the signal it is hunting, which is why Webb hides behind a tennis court-sized sunshield that keeps its instruments chilled to nearly 400 degrees below 0 Fahrenheit. Webb can detect the heat signature of a bumblebee at the distance of the moon. It is the most sensitive eye humanity has ever created. Su's team won time on this machine to hunt down their mystery X-ray sources, and one of them was a faint speck cataloged as LID 568. Now here's a detail that matters more than it first appears. Because LID 568 was essentially invisible in earlier images, the team could not pin down its exact position well enough to use Webb's standard spectrograph, which needs precise coordinates. So they made a practical decision. They used an instrument mode called an integral field unit, which captures a spectrum for every single pixel in its field of view at once. Instead of one narrow measurement, they got a complete 3-dimensional map of the light around the target. It was a workaround, a bit of instrumental improvisation to solve a targeting problem, and it turned out to be the luckiest decision of the entire program. Because without that full map, they would have completely missed what was happening around this object. When the data arrived, the first surprise was distance. LID 568 was not just far away. Its light had traveled for roughly 12 billion years, meaning the team was seeing it as it existed about 1.5 billion years after the Big Bang, deep in the era when the universe's first galaxies were still assembling themselves out of primordial gas. This was the cosmic dawn, a period astronomers have been desperate to study, because it is when everything we recognize today was first being built. The first generations of stars were burning through their fuel and exploding. The first heavy elements, the carbon and oxygen and iron that would one day make planets and people, were being forged and scattered. And somewhere in that chaos, the first black holes were beginning their climb toward becoming the giants we see today. The second surprise was the black hole itself. Hidden inside a small, unremarkable dwarf galaxy sat a black hole of about 7 million solar masses. That might sound enormous, and by everyday standards it is. But compared to the billion solar mass monsters of the early universe, this was a lightweight, a black hole caught in an early stage of its growth. For the first time, astronomers were not looking at a finished giant and wondering how it got there. They were looking at one in the middle of the process. And then came the third surprise, the one that made the team check their numbers again and again. When they compared the black hole's mass to the staggering amount of energy pouring out of it, the feeding rate came out to roughly 40 times the Eddington limit. 40 times the theoretical maximum. To put that in perspective, imagine clocking a car at 12,000 miles per hour on a highway with a 300 mile per hour speed limit. Your first assumption would not be that the car is fast. Your first assumption would be that your radar gun is broken. So the team went looking for the mistake. This is the part of science nobody makes movies about, but it is where discoveries live or die. For months, the researchers attacked their own result from every angle, trying to kill it before someone else did. Maybe the mass estimate was wrong. Maybe the brightness was being boosted by something else. A hidden companion, a gravitational lens magnifying the light, a burst of star formation masquerading as a feeding black hole. Maybe they were seeing two objects blended together. One by one, they ruled the alternatives out. The distance held, the mass held, the energy output held. But the data kept holding up. And the strongest evidence came from that lucky instrument choice. The integral field unit revealed enormous outflows of gas erupting from the black hole, plumes of material being blasted away at high speed. Exactly what you would expect if a black hole was gorging itself so violently that it was flinging food off the table. Those outflows were the smoking gun. This was not a measurement error. This was a black hole caught red-handed in the middle of an impossible meal. The result was published in the journal Nature Astronomy in November 2024, and it sent a quiet shockwave through the astronomy community. Because if a black hole can genuinely feed at 40 times the Eddington limit, even for a short while, then the seed problem, the 20-year-old mystery of the impossible giants, suddenly has a way out. Here is why. Remember, the whole problem was time. Stellar seeds are too small and the Eddington limit is too slow for them to become billion solar mass giants in under a billion years. Astronomers had proposed two main escape routes. The first is called heavy seeds. The idea is that in the early universe, gigantic clouds of pristine gas might have collapsed directly into black holes of 10,000 or even 100,000 solar masses, skipping the star stage entirely. Bigger starting point, less growing to do. The second escape route is cheating the speed limit itself, a process called super Eddington accretion, where under certain chaotic conditions, matter crams into the black hole faster than radiation can push it away. Theorists had modeled it. Simulations suggested it might be possible in short, unstable bursts, but nobody had ever clearly caught a black hole in the early universe actually doing it. LID 568 changed that. Its feeding frenzy demonstrates that super Eddington accretion is not just a theorist fantasy, it happens. And the implications are enormous. If black holes can grow in violent bursts, gorging at dozens of times the normal limit before settling back down, then a single feeding episode could accomplish what standard theory says should take hundreds of millions of years. A black hole could gain a huge fraction of its final mass in one brief, spectacular binge. The impossible giants of the early universe stop being impossible. They just become the survivors of a violent, all-you-can-eat childhood. Interestingly, the discovery does not kill the heavy seed idea either. The mass of LID 568's black hole, caught mid-growth, is consistent with either starting point, a light seed that binged its way up, or a heavy seed doing the same. What it proves is that the binge itself is real. The universe has a fast lane and black holes use it. Now you might be wondering how a black hole gets away with this. If the light pushes back harder the faster it feeds, how does anything break the limit at all? The leading explanation is beautifully simple. The Eddington limit assumes the situation is tidy, with radiation streaming out evenly in all directions and pushing against all the incoming gas equally. But a real feeding frenzy is not tidy. The disk can become thick and turbulent, and the radiation can get funneled out through certain channels like the poles, while matter continues to pour in along the disk itself. The light escapes through the chimney while food keeps coming through the door. The result is a black hole that is technically breaking the speed limit while every individual photon obeys the laws of physics perfectly. Nature, it turns out, does not break its own rules. It just finds loopholes. And this is where the story connects to something much closer to home. Because the growth of black holes is not some isolated cosmic curiosity. It is one of the forces that decides whether galaxies become places where life can exist at all. Nearly every large galaxy we know of, including our own Milky Way, has a supermassive black hole at its heart. And those black holes are not passive residents. When they feed, the energy they release sweeps through the entire galaxy, heating gas, driving winds, and in extreme cases, shutting down star formation altogether. A galaxy's black hole helps decide how many stars form, where they form, and what elements enrich the clouds that new planets are born from. The calm, orderly disk of the Milky Way, with its quiet neighborhoods where a planet can circle the same stable star for billions of years, exists partly because our central black hole grew the way it did and settled down when it did. Consider our own situation for a moment. At the center of the Milky Way sits Sagittarius A star, a black hole of about 4 million solar masses, remarkably similar in size to the one in LID 568. Today it is quiet, sipping only thin wisps of gas, and that quietness matters enormously. A violently feeding central black hole floods its galaxy with radiation and high-energy particles that can strip atmospheres from planets and sterilize entire regions of space. Astronomers who study galactic habitability talk about safe distances from an active galactic center, much like habitable zones around stars. Earth sits about 26,000 light-years from our black hole, far enough that even its ancient outbursts, and there is evidence it had them, washed over our neighborhood as a whisper rather than a scream. We won a lottery we never knew we entered. The outflows Webb spotted erupting from LID 568 are that process, caught in its rawest form. That black hole is not just growing. It is reshaping its host galaxy in real time, blasting away the gas that would otherwise become future stars and future worlds. In a very real sense, when astronomers study how the first black holes grew, they are studying the opening moves in a game whose endgame is habitability. The violent childhood of a galaxy determines what kind of adulthood it gets, and whether that adulthood includes quiet suns, stable orbits, and rocky planets with liquid water. The search for life does not begin with planets. It begins with understanding the engines that build the galaxies those planets live in. There is one more thread to this story, and it might be the biggest one. LID 568 is not alone. Since Webb began operating, it has been finding small, mysterious objects scattered across the early universe that astronomers have nicknamed little red dots. Hundreds of them. Many appear to be compact galaxies feeding black holes that seem too massive for their surroundings. Black holes that are strangely overweight compared to the galaxies they live in. In the modern universe, a black hole typically weighs about 0.1% of its galaxy's stars. Some of these early objects host black holes that make up a huge fraction of their galaxy's total mass. It is as if the black holes grew first, and the galaxies had to catch up, the exact opposite of what older theories predicted. If super Eddington bursts like the one powering LID 568 are common in the early universe, the little red dots suddenly make sense. They could be an entire population of black holes caught in their binge phase, growing ahead of schedule, ahead of their own galaxies, ahead of everything. Sood's team has already secured more time on Webb to observe LID 568 again, and other groups are now hunting for more objects like it. Every new example will tighten the picture of how long these feeding frenzies last, how often they happen, and how much of a black hole's final mass they can supply. The follow-up observations will focus on those outflows, the plumes of gas the black hole is hurling away. By measuring their speed, their extent, and their composition, astronomers can effectively run the clock backward and estimate when this binge began and how long it can continue before the black hole blows away its own food supply. Some models suggest these super Eddington episodes are self-limiting, lasting only a few 100,000 years, a blink in cosmic terms. If that is true, then catching LID 568 in the act was like photographing a lightning strike with a single random snapshot of the sky. The odds say there must be many, many more strikes happening across the early universe for Webb to have caught even one. And the honest answer, the one every good scientist on these teams will give you, is that we do not fully know yet. Maybe LID 568 is typical, and the early universe was full of black holes gleefully ignoring Eddington's ceiling. Maybe it is a rare freak, a one-in-a-million object that Webb happened to catch at exactly the right moment. Either answer would be profound. If it is common, we have solved the seed problem. If it is rare, then finding it among the first handful of targets means the universe is far stranger than our models allow. But step back for a moment, because there is something worth sitting with here. The Eddington limit was calculated a century ago by a man working with pencil and paper, decades before anyone had proof that black holes even existed. It survived every test we could throw at it from the surface of one small planet. Then we built a telescope, folded it up like origami, launched it 1,000,000 miles from Earth, and pointed it at a smudge of light so old that its journey began before our sun was born. And in that ancient light, we found the exception. Not a violation of physics, but a deeper layer of it, a loophole written into the universe from the beginning, waiting 12 billion years for someone to look. Every generation of astronomers inherits a universe that seems mostly explained, with just a few loose ends. And every generation discovers that the loose ends were the whole story. A dim X-ray source that nobody wanted to study, a targeting problem that forced a lucky instrument choice, and suddenly a 20-year mystery about the largest objects in existence has a crack of light running through it. The black holes that anchor every galaxy, including the one that anchors ours, including the one whose ancient tantrums helped shape the quiet corner of space where our planet formed, grew up faster and wilder than we ever imagined. We are, in the most literal sense, downstream of that violence. If this story blew your mind, hit the like button, because it genuinely helps more curious people find this channel. And subscribe, because next time we are looking at the galaxies Webb found at the very edge of the observable universe, galaxies so large and so early that, according to every model we had, they should not exist at all.